So, next part here is the asset server. So, I'm gonna give the basic idea behind the asset server is for the engine to take more responsibility for editing files. So instead of the editor editing files directly on disk, it will talk to the engine in terms of the asset server, which is also the compile server and the file server, sort of general server copy of the engine that we start up, and tell the engine to save a particular file or load a particular file and so on. And I'll get into why we want to do that. But let's start by looking at how it works today when you work with the editor. So currently we have the workflows we have are disk-based. So everything goes through the hard drive, and it's also based on the file system. So when you each resource that we have in the engine corresponds to one file on the disk, as I talked about in a previous talk. And when we kind of like that approach because it makes, I mean, an alternative would be, instead of having one file for one resource, an alternative would be to have a big opaque database, and you wouldn't actually, in the file system, you wouldn't actually see what resources you had or what they were named and so on. And that can be kind of nice because we can sort of hide things from the user, and we don't have to worry about the user moving stuff around on the disk or renaming stuff on the disk or doing whatever on the disk. So we could just use a SQLite database and hide everything in there. And it would be kind of nice for us, but it would also suck a bit for the user because they wouldn't have any overview of what the files were. They couldn't actually go into and look in the files. They couldn't edit the files using their ordinary editors. They couldn't use normal source code version control tools like Git or Perforce or whatever to manage these files, because it would just be a big opaque SQLite blob that they couldn't really work with. So even though it would be nice for us, I think supporting these disk-based workflows with like one file per resource is really nice for the user, even though it's kind of a pain in the ass for us, especially with things like Windows file locking and stuff like that can totally trip us up randomly. But anyway, so what we have right now are completely disk-based workflows. So when the editor wants to, when the user works on something in the editor, the editor loads up a file from the disk, you edit something in it, and you save that file back to the disk. And then to get that into the engine, we have the data compiler, takes this source file, compiles it into a binary runtime format, saves that binary runtime format to disk. So it loads the source from disk, saves the result to disk, and then when you run the runtime, it will load this compiled thing from disk again. So there are a number of problems with these sort of disk-based workflows. One is latency. Touching the disk takes time. Just seeking on the disk or getting a file from the disk, writing to the disk, loading from the disk, there's a certain overhead there with that stuff. And while it's fast enough for some operations, it's not fast enough for things like dragging a slider. So one scenario that we would like, for instance, is if you, or that we have already in the editor, and that you definitely want in the editor, is, say for example, you're editing your sky dome and or your light simulation, and you sort of change. You have a slider that represents the strength of the sunlight. As you drag that slider, you want to kind of immediately see that change being reflected in the world. And there's no way we can do that fast enough with this disk round trip. Just writing the source file to the disk, then compiling it, and then loading it is not fast enough to respond to the slider. So the way it kind of works now is for everything that needs that kind of immediate feedback, where you drag the slider and you see the result immediately, we have backdoors. So when you drag the slider for the sunlight strength, we won't actually save a source file, compile it, and then reload it. We'll have a path where the editor directly tells the engine, oh, you need to change the color of the sun or the intensity of the sun by this much. So, and we need special paths for each of these workflows, which is kind of a pain in the ass to write and maintain all these special hooks into the engine. So that's a problem. Another problem is that the editor will want to preview stuff before you save the file. So if you're editing a unit or a level or whatever, you want to see the results of your edits. You want to see what the unit looks like with your edits before you have actually saved it and sort of committed those changes. So you want to see the changes in the viewport before you've saved the file to disk, which kind of creates a problem with this workflow where everything is based on actually having the saved file on disk already. And we actually work around this in sort of ugly ways. So some of our editors, the unit editor for instance, will actually create temporary files on disk to represent your sort of unsaved edits. So it will create a new temporary unit on disk to represent your the edits you've made but not yet saved, and that temporary unit will get compiled and loaded, and it's that temporary unit that you will actually see in the viewport instead of the unit you're currently editing. But it's kind of ugly, and it also means that if your editor crashes for whatever reason, you will have these temporary files still left on disk, and it's not a very nice solution. Another problem is that if you have multiple editors or multiple runtimes running, they're all running against the same disk folders, which means that the state is kind of unclear. Because say that you've launched the game, you've launched a runtime, and it's running from your compiled data, and then in the editor you do some changes, save something, and trigger a new compile. Now the new compile will start overwriting the runtime data. It will start generating new runtime binary files, writing them down to disk, not really caring about what is already there, overwriting those files. At the same time, the runtime that's already up and running might well be in the process of reading those very files. And if those files are written at the same time and it's reading it, we may get a crash, we may get problems with Windows file logs and stuff like that. So it's kind of a messy and unclear situation when you have multiple writers and readers touching the same files on disk. We also have the problem that writing tools is kind of complex, because since we can't rely on the file path, as I said before with dragging the slider, we need all these explicit other paths for synchronizing the state between the editor and the viewport. So we have to have things like when you drop something into a level, we have to explicitly talk to the engine to spawn that thing in the level. We can't just say, oh, here's an update to the level, just display that update. We have to explicitly spawn it, and a lot of the tooling code deals with that kind of explicit synchronization between the editor and the engine. And if you make a mistake, they will desynchronize, and you will get all kinds of errors. And another problem, finally, is that we don't have any good way to do collaborative editing. We don't have any way to have We can't have multiple collaborators touching the same file on disk. That will create problems. So, and we eventually want to support collaborative workflows, but this with this disk-based system, we don't have any good way of doing that. So all these things are the things that we want to fix by moving through the asset server. So what's the idea here? The idea is to move responsibility from the editor of taking care of files on disk and so on, and moving that responsibility more to the engine, so that the editors become easier to write and we can actually synchronize the different things that the editors do. So with this approach, moving to the asset server, the editors will no longer talk directly to the disk. They will no longer directly read or write files to the disk. Instead, they will talk to the asset server. And the asset server is it's just our engine running, and our engine running in asset server mode. And when the engine is running that mode, it starts multiple servers. It has a file server, so consoles and other things can load files from it. It has the compiler server, so different system can request compiles, and it also has this asset server used for loading and saving source resources to the disk. So instead of saying load save directly to disk, the editors talk to the asset server. So when they want to save, they can either when they want to save a file or change a file, they can either say send the complete new content of the file, or they can just send delta JSON. If they just want to make a small change to a file, they can send delta JSON representing that particular change, and that change will then be applied by the engine, and the JSON file will be saved with that change. The asset server has an in-memory state with an explicit save command. So all the source resources, so the asset server can represent unsaved state. So when you change something in the editor, it will change the in-memory state in the asset server, and then to actually save the file to disk, you send save to the asset server, and then this in-memory state that the asset server keeps track of will be written down to disk. But the asset server knows this in-memory state, and when you compile the data, it will compile the in-memory state into in-memory binary data. So this has so we do this. We can do this without touching the disk, and we also can compile sort of this transient state that hasn't been saved yet. And the file server can also serve directly this in-memory binary data that we compiled from the in-memory source state. Clients, which includes editors, in addition to saving and loading files with the asset server, they can also listen to changes. So when a client is connected, it will actually be notified by any change made to any source file. So for example, if an editor will get change notifications when a particular file has changed, and then it can update the UI. If some value changed, it can change that value in the UI and display it. So the editors work that way, and the editor viewports, sort of what you see in the editor where we're running the game, acts as just another client. So instead of having the editor send these explicit Lua commands to synchronize the state to the runtime will just be another client to the asset server. It will listen to changes from the asset server and update its state accordingly. So that means we get rid of all this explicit state synchronization, which is such a pain to write, and instead the runtime will just be responsible for listening to state changes and showing them. And we can have multiple, since we're doing all this, everything is now done with a network connection. That means we can have multiple editors connecting to the same asset server and multiple viewports connecting to the same asset server. And it will all work the same way. For the editors, it doesn't matter if these changes come from the local machine or from a remote machine. It will work exactly the same way. It will just be changes sent over the network, and then those changes will lead to change notifications that are sent out to all listeners. So as we can see, this actually solves all the problems that we had up here. It solves latency because we're no longer touching disk. We're just going through memory. The changes are happening in memory, the compiles are happening in memory, everything is loaded from memory. So we get much faster latency. And for slider operations, it might not still be fast enough to go through an entire compile cycle. It might be for some resources, maybe not for all resources, but even for the resources where this is not fast enough, we can still make it work with this system because we can listen to the delta JSON changes and react to those. So we can react to slider changes as a delta JSON change and show that effect immediately in the engine. This is fine. We don't need to save a file anymore to compile it because we have an in-memory state representing the file, so we can preview unsaved changes to files. The state is I will talk a little bit about this later, but this we will solve this too. We don't need the explicit synchronization, so writing tools will be a lot simpler. Collaborative editing is no longer a problem, which is perhaps the most interesting things of all of this, because we no longer care where a change to a file comes from. It can come from the local editor, and we'll send out the notification, we will update our viewports and so on. It can come from a remote editor, we'll do this exact same thing. So with this system in place, collaborative editing will actually just work, hopefully, which is really exciting. Also, a change can actually come from the disk too. So the disk will be, in this system, the disk will be just another editor. So the asset server will start a disk notification listener that listens to disk changes, and if it detects a change on the disk, that change will enter this system exactly as if that change had come from an editor. So that means that in addition to using the editors, in addition to using the local editor, possible remote editors, you can also edit the files directly on disk and save them. And when you edit the file directly on disk and save it, it will enter the system exactly the same way, notification will be changed, editor UIs will be updated and so on, which is really nice. So you can run, if you have like some Python script that manipulates 1,000 resources, you can run that and the UI and everything will update and show those changes, which is actually super nice. And if you git sync, for instance, you pull new project content over from Git, those Git changes will come to the disk, and then they will come in as edits from the disk as everything else comes into the system, and everything will just be updated to reflect those changes too. So the nice thing about this is that we still get to keep all the nice things we had about having a disk-based system. You still can edit files directly on disk, you can still use your regular version control tools and everything that you want. In fact, it's a lot better because you can edit the files on disk and the editor will immediately reflect those changes, which is pretty amazing. So the implementation of this, the asset server, actually we've already sort of covered most of the implementation of this when we talked about in the file system talk, like the IO file system talk. because most of this is implemented by the iDatabase class that I talked about in that talk. The iDatabase class, as I said, it represents a disk source with a memory overlay, so you can have memory edits to disk source files. And it listens to changes on the disk, as I just said, and it has a server thread that takes these sort of change messages from clients and forwards it to the database. So when the client says write this file, it will be changed in the database. And when the client, which in this case is the editor, says save, it will save the file and so on. And it will send out notifications to the listeners when files change. The Delta JSON thing is kind of interesting here. So we support both writing binary content of files, like here is the full content of the file, I'm sending it. And we also support these Delta JSON operations. Now, in the notification system, you will only get a Delta notification if you do a Delta write. So if you write, so you can edit a JSON file and write the whole file out, say just here's the entire content of the file. Then the listeners will get a write notification. They won't get a Delta notification, so they will have to react by reloading the entire file. So you can sort of decide, but if you just do a small change, you can send it as a Delta JSON change, and then the clients will get Delta JSON notifications, and then they can hopefully react. Then the clients can decide, oh, do I want to reload the entire file, or will I try to just handle this small change in order to get a faster update so that you can do things like automatic reaction to sliders and so on. So as a writer, when you're writing a system, you can sort of decide on the level of granularity you want to work on, if you want to support these Delta JSON workflows, or if you just want to support full reload and full recompile of files. And that kind of depends on the files. I'm kind of thinking that it will be mostly level files that will support the Delta operations, because the level files are kind of big, and still you want fast reactions to spawning something or dragging a slider. While as for most other systems, such as editing units and so on, I think we will be fine with doing a complete edit and complete compile and reload cycle. So we can recap a bit in this database. An abstract interface for representing a collection of files. We can get the paths, can read and write content to a particular path. Remove, it also keeps track of hashes, so we can easily see when something's changed. And then we have the mounted version of this that I talked about in the previous talk, where we can mount different directories. And this is actually what is exposed by the server. So the mounted version also has the in-memory, the sort of dual representation. It knows the disk state, but it has a transient memory state. And it supports operations for saving, so that we can save the in-memory state down to the disk. And it also supports a revert operation, which means we will throw away the in-memory state and revert to the disk state for a particular path. So the implementation of this, this is kind of a big file because it has a lot of stuff in it. But it has different implementations of databases. It has a memory database which has no disk representation. We just store the content of each files in memory, just hash from the path to the file content. And then we have disk database that also implements this, where the files are stored on disk, and we use a directory watcher to detect changes of disk. and we start with sort of like indexing the entire disk, and we have a cache for remembering the hashes of all the files, so we only update it if we detect the file change. And it implements the database interface for the disk. Then we have this mounted version, which will use a memory database for the unsaved changes. So that's the transient changes will be saved in this memory database, not to disk. And then it has a number of mounts for representing all the mounted databases, which can be either disk bases or more memory database. You can actually mount a memory database at some point here too. And then it too implements, I'm not going into the details, but it implements the interface here. And then, yeah, I should show the notification part of the interface too. This is the notifications. It's based on polling. We usually prefer polling rather than callbacks in the Onion because it's more controlled. You know, when you poll, you know exactly when you do it, and you know exactly when you will get the results back. Whereas with the callback, it's always a bit uncertain when the callback will happen and what state you're in. So we prefer polling. And also since in game development, in game projects, you have a regular tick, so you have a regular place to poll, whereas in some other kinds of applications you may sleep indefinitely, so polling might not be as good because you don't have that tick that is a natural place to poll your systems. Anyway, this is a way you get notifications. You call it to get all the changes since a particular version, and you get back a list of all the files that have changed since that version, and then you get a new version. And this version number will increase every time something changes. So this way you can sort of query the change history and find out when stuff changed. Yeah, then we have the database server here. So the database server keeps track of these databases, allows the client to connect to them, and then it has a command processor somewhere here. Let's see. Here, where it receives commands from the client, like connecting to a project, listing paths, reading files, writing files, saving, reverting, deleting, and so on. Just takes those commands from the client and converts them to commands to the database. There's also a notification somewhere here. Let's see. Yeah, here it sends, in this loop where it updates the client, it gets all the changes, and it sends change notifications to the connected clients. So that's it for the database. The other component of this that I also talked about in the file system talk is the file system cache, which is used for this, for the output from the data compiler. So we don't save the output immediately to disk because we don't want to touch disk. Instead, it's saved in memory temporarily while it's being flushed out to disk. So this sort of caches the result of the compile until it can get written out to disk. And the file server will serve from this cache, so we can serve the result of the compile immediately before the compile is finished. So the asset server is currently a work in progress. We're working on the Onion side of it. It's not that much left to do on the Onion side. It's a little bit to do in the Onion side, and then there's a lot of work to be done on the editor side in switching all the editor workflows over to using this asset server instead of the disk-based workflow. So that's the big chunk, rewriting the tools to work against the asset server. That work has actually been started. There are tools like, I think the new particle editor works directly against the asset server, and there's work to bring more tools over to this. Left to do on the onion side, one thing left to do is to start dealing with the concept of versions of the compiled data. As I said before, we have this problem when we have multiple editors and multiple runtimes all reading and writing the same compiled data. That leads to all kinds of race conditions and crashes and file locks and so on, which is really bad. So we need to get away from this. So for this to work, we need to be able to represent multiple versions of the same compiled data in the compiled data directory. So it should be possible to compile your data at some point in time and give that compiled data version number, say version number 18, and then you start a runtime, an onion runtime that loads that data. So the onion runtime will then run with compiled data at version 18. Then you do some changes to the source data, you add some stuff, do some stuff, do another compile. That compile becomes version 19. That compile should not disturb any of the resources of version 18, because we don't want to fuck it up for this runtime. This runtime should still be loading version 18 from this, so we don't want to mess with any of the files that this runtime might currently be using. So the new compile writes 19, and then we can start a new runtime that says, oh, this runtime should be loading version 19. It will load only version 19 resources and won't mess with any of the other stuff. Or we might send a refresh command to the old runtime and say, well, you were previously at version 18 of the compiled data, but now you should update to version 19. So please reload all the resources and update yourself to version 19. And the way we're planning to do this is we don't actually want separate the disk directories for version 18 and version 19 and version 20. We could do that, but since the compiled data can be pretty big, it can be multiple gigabytes. If we had to write out all this compiled data for each version, it would take, our compile times would go through the roof just from copying data on the disk. So we definitely don't want to do that. So what we want to do instead is that we want to switch the format of the data directory to contain files that are hashed, files that are indexed by the hash of the file content. So the same file content will always have the same name, which will be the hash of that file content, which means that if you compile a new version, all the resources that haven't changed will still be the same. They will be the same resources and have the same name, and they won't be touched at all. If a resource has been changed, we will create a new file because the changed resource will have a different hash, so it will get a different name, and that new file will then be stored in the compiled folder together with the old version of the file, which would still have the old name. Then, of course, at some point we need to do kind of a garbage collect operation to collect all the old files that aren't used anymore. But we want to leave them around for a while because they might be used by any running onions, because an onion might be running to an old version of the data. So if you're familiar with Git, this is kind of similar to how Git stores objects and blobs. We will essentially have a Git file system representation of the compiled data. So that will take care of this, but that's something we still have to do. Another thing we want to do is to look a bit more at speeding up the file server, because currently when we're running on Windows, the Windows runtime is loading data from disk, directly from disk. It's not loading data through the file server. And the reason for doing that is that loading data locally from disk is a bit faster than loading it from the file server. And we generally want to be as fast as possible. That's how we like to do things in the Onion. But loading data from disk means that we lose these benefits. We lose the benefit of being able to reload the data immediately from this in-memory state in the file system cache. Because the server will serve directly from the file system cache, but of course that data hasn't been written out to disk yet. So we lose that sort of nice latency, and we'll have to wait for the file to actually reach disk. I looked into this a bit. I've done one optimization pass of this and actually speeded up the file server a lot, but it's still maybe 40-50% slower than loading directly from disk. I'm not sure it has to be, because networks are pretty fast these days compared to disk, especially on localhost. But when I looked into this, it seems like most of the delay was in the Windows TCP/IP layer, which makes it kind of hard for us to do anything about. So it may need some investigation to see if we can speed it up any further. If we can't, one alternative would be to sort of start up the onion in disk mode, so it will read the bulk of its data from the disk, and then sort of once it's been initialized and read the bulk of its data, we can switch it over to file server modes and sort of get the benefits of the fast latencies and the immediate compile, but still have the bulk of the load happen with the slightly faster disk-based routine. But if possible, I would like to go to loading everything from the file server, just because it's neater to have everything go through the same system. But 40% decrease in load times can be pretty long when you have a big project, can be minutes. So I don't think we're willing to pay 40% extra load time. So we might have to do this sort of hybrid solution instead. The asset server hasn't been taken up into full production yet, so I think there's still some stability things that need to be evaluated. It needs more debugging, more testing, more performance testing, and so on. But not a ton of stuff to do on the Onion side, at least, until we're ready to switch over to this system completely. Any questions on this?
Hey, Nicholas, thanks for the talk. I have a question regarding the asset server and its responsibility in terms of managing references. The way I understand it right now is there's no any concept of reference in the asset server, and when you have a string that is a reference for like a file name, is up to the editor to handle the tracking of all the references in all files, and to write a data JSON that updates everything when a rename occurs. Is that correct?
Yes, that's correct. And it's a pretty bad thing that we're not distinguishing between reference and just other strings, other JSON strings. So we have no way of knowing or detecting when we have references, which limits which means we can't do automatic reference patching, sort of. It all has to be based on semantics. The one who's doing the reference patching needs to know the semantics of all the files, which is pretty bad. I think I talked a little bit about this in some previous talks about IDs versus names and so on. But what we want to do, and which is actually planned but hasn't been started yet, but which is actually planned, is to move the responsibility from the responsibility of the dependency tracking from the editor to the onion, so that it will actually be the onion that keeps track of all these dependencies, and the onion will know, or the references, I should say, rather, and the onion will know all the references and where all the references are. So the responsibility is not on the editor, and then we can probably process these references more efficiently.
So this means that the asset server will use the engine capabilities of managing that to, for example, at some point, just I do a rename from the tools, just one simple call.
Yes.
And then the asset server will take responsibility to write everything on the disk everywhere it matters, right?
Yes, exactly.
Okay.
Exactly.
Okay, thanks.
And another thing that I know has come up, that people have asked about, is like undo, how undo should work, which is, should undo be the responsibility of the engine? Should the engine sort of keep a history of the files and undo automatically, or should it be the responsibility of the editor? And I think we come to the conclusion that it should be the responsibility of the editor, because the editor has the sort of context to determine what is a proper undo operation. There's also the discussion of how to do undo properly in a collaborative editing environment, which I won't go into here because that's kind of a hot potato and something that you can spend way more time than we have for this talk to just talk about. Anything else?
I have a small question about the collaboration scenario. So we will have one asset server and maybe 2 editors running. So will every changes, even dragging the slider on one editor, will be reflected on the other editor, or all the changes will be committed to the other editor only when the level is saved?
No, I think we want to commit the changes immediately. I think the sort of I think there are two modes of collaboration in general, which are both useful, which are sort of online and offline collaboration. So offline collaboration, that's more like Git collaboration. I edit separately, then I save, and you get the changes. You edit separately, you save and commit, and I get the changes. And then we have online collaboration, which means we are actually in the same state, seeing the same stuff immediately, like Google Docs style. So when we're talking about, so offline collaboration we already have. We already have like Git support, you can, or whatever version control system you want to use for your project, and merging and stuff like that. We already have support for that, and that's not something that we really need, or that really brings anything more to us by adding more support for that. So I think the thing that we really need is the online collaboration, being in the same workspace at the same time. I think that's sort of the value add that we will get from this. So the way I see it is that in memory state will be reflected immediately between all the clients collaborating. Even the transient state will be reflected immediately.
Does that mean that, as you say, that the file system, the disk, will be at another editor? For instance, if I pull a file from Git, it will be all the editor running will see their assets overridden by the new version of the disk.
Well, the way it will work is that one person, or perhaps a central system, but some computer will act as a server. And that server, where the assets servers run, that is the state. Your disk, if you connect to the server, your disk won't be touched. You don't even need to have the project on your disk, because you will be loading everything, saving everything through the server. So you don't even need the project. You're editing in the context of the server. And the server, everything that saves, if you save something, it's saved on the server's disk. So you're editing in the space of someone else, sort of.
Yeah, so that means that if this someone else maybe change the file on disk or erases the file on disk, what I did can be completely lost.
Yeah, totally. That's sort of what you accept when you edit in the same state. You're accepting that anyone else can mess around with your stuff, and so
you have to trust other people.
Yeah, exactly. I mean, that's the benefit and the disadvantage of it. That so I don't think you can get the benefit of collaborative editing in the same state without also getting the disadvantage of it. So it might not be for everybody to these kinds of workflows. I think we will see some people may not like that kind of collaborative workflow at all. It might seem just too out of control. Certainly, I wouldn't like that for source code. I definitely like the offline model for source code because I have something stable that I can actually compile and not 50 people changing my source code files all the time. So it's definitely not for everybody, but I think for some people and for some use cases, the collaborative, the online collaboration model is super, super useful. Like when you're in a Google Doc, like it's very, very much more convenient than doing sort of change reviews with Microsoft Word, which is sort of the offline version of that. So I don't think we should say that collaborative editing, I think if we're talking like strategy for the Onion long time, I don't think we should say that it's always collaborative editing. That's the way you work with the Onion. You always have to work collaboratively in the same state with everybody, because a lot of places will not want to do that, especially if you have like 50 people at the game company. They won't want to be working in a situation where anybody can break your stuff all the time. But what you might see instead is that small groups of people, like 4 people, may sit down and work together on a level in the same state, and then sort of commit their changes in an offline way to the rest of the group.
Okay, thanks.
Anything else? All right, talk to you tomorrow again. Yes.
Thanks, Niklas.
Yes.
Thank you, Niklas. Bye-bye.
Bye.
Thanks, bye.